Hi, my name is FIRDAUS bin Mohammad NAZRI, and today I'll be presenting my final year project for Pixel 2021. The title of my final year project is Movement Estimation Using Artificial Intelligence, or in short, METAL. So this is the basic outline for my presentation. I'll be discussing on the project background, problem statement, project objectives, proposed solution, design of solution, project implementation, and finally the impact and benefits. So first of all, for the project background. So the background of the project is that there are numerous marker-based motion capture solutions in the current market. And for this marker-based motion capture, markers are attached to the body suit, and these markers will act as sensors to provide input to the motion capture software. And once it's done, it will calculate the angle and velocity of the body joint. However, marker-based motion capture is costly and tedious in terms of setting up the system itself. So the problem statement for this project is the first one is it is expensive and extensive setup for marker-based motion capture. The second one is there are existing solution that does not provide a clear indication when a wrist-prone movement is being performed by a user or a subject. And the third problem statement is that these existing motion capture systems have a hard time capturing motions that are fast-paced or when the subject is wearing a loose clothing. Loose clothing means that they're wearing baggy shirts or shorts. Okay, next is the proposed solution. My solution is it consists of mainly three main modules. The first one is the deep learning algorithm for joint detection. First, of course, we have to detect the joints of the subject. The second module is the calculation module, which is to calculate the angle and velocity for each joint that is located on the subject's body. And the third module is the user interface module, which is to ease the process for user to select videos and so on and so forth. So the next one is the objectives. The first objective is to integrate deep learning method for estimating accurate skeleton joints. The second objective for this system is to measure the velocity and angle at each skeleton joint in every successive frame. This means that for a given video that a user selects, the system should be able to capture the angles and velocity for each frame that is available in the video itself. And the third objective is for the system to automatically identify a wrist-prone injury movement. So this is the solution design in terms of the module diagram of the system. The first one is of course the algorithm for deep learning, which is to detect the joint for the participants or the subject. It should be done using supervised pre-trained model, which I will explain more later. And the second module is the calculation module. Calculation module is responsible to calculate the angles and velocity for each successive frame, as I've mentioned earlier. And the third module is the user interface module, which is the module where I have to design how the system would look like for the user. Okay, so next is the application architecture of the system. I've divided the application architecture in terms of the front end and back end of the system. So for the front end, you can see there are account management, which the user would first either create or log in to the system, and it would then authorize or depending on the credentials provided by the user, it would grant access to the system. And if the system has granted access for that particular user, you then proceed to the video selection module, where the user would select the video that they wish to process, and it will go after they select the video. It would then go to the video processing module, where you would detect the joints for the subject and also perform angle and velocity calculation for each frame and for each joint. Then once all of the frames have been processed, it would then proceed to the output processing module, where the array of images that have been processed will be appended into a video format, and also the array of values for the angles and velocity would be then converted into a CSV file, which is used for, let's say you want to compare with other values, or if you want to or if the user wants to do further analysis, they can use the CSV file. And after the output processing is done, it will then proceed to the project folder selection, where the user would be able to select which project folder or the name of the project and which directory they wish the project folder to be in. This is being done to prevent overwriting from happen. So sometimes when if a user selects a name that is already existing in the system, it might overwrite the value if we don't perform this kind of checking. So once the project folder selection is successful, it will then proceed to display the final output file that has been produced by the system. Okay, next I'll be explaining a bit about the algorithm for the modules that are involved in this system. The first one is the joint detection module. So the joint detection module is actually used by a pre-trained model that is also supervised, that is from Google's mediapipe BlazePose. So it is, as I've mentioned, it has been pre-trained. That means Google has already trained it with around 85,000 images that they have collected. Which is supervised. That means they have already annotated the images, the 85,000 images, as to where all of the joints are located to train the model itself. So the basic concept is actually based on Vitruvian Man. As you can see on this screen, this is a concept that was originally proposed by Leonardo da Vinci, the famous artist. And what what Google has done is that they have employed a two-step detector tracker, as you can see on this right side of this screen, where it would first take the video source and it will process the first frame to get this region of interest, this area of a circle. So what they have to find is first the middle heap and the top point. That means once they can get this region of interest, they will be able to calculate the joints to detect all of the joints that are present on the image itself. So once the first step is for it to detect on the first frame, and then consequently for other frames, the second and third, it would just simply derive the region of interest. Since when let's say in a given situation of a video recording, a person is moving in a video, so the first frame is where the original source, the original place of where the user is at, and for the remaining of the frames, it will just simply derive the previous location. So this is being done to avoid like unnecessary calculations, and this has been proven to be more computationally efficient, and it saves more time as compared to calculating everything over and over. So that's for the joint detection module. Next is the calculation module. I employ this formula, the cosine, the law of cosines. Is also a popular mathematical formula. Whereas given there's a three-side triangle, you can find the angle of interest. For this case, for this formula, on the left side you can see the capital A. Let's say if you want to compute the angle that is located at A, we need to first get the distance of A, B, and C and plug it into the formula, and we'll be able to get the angle. So the concept of this calculation is that let's say let's just assume for a person, the C is the right shoulder, A is the right elbow, and B is the right wrist. So once we can detect these points, which will be done by the joint detection module, it will then get this point and calculate the distance between of all these sides. So if we can get all of these sides, we can also get the angle of the, let's say for this case, if you want to find the angle of the elbow, you will be able to get the angle using this formula, given that we need to first have the length of these three sides, which we can get by once we detect the location of the joints using the joint detection module. We can then take the x and y coordinates to find the distance between all of these 3 points. So we can then put it in a three separate variable, the a, b, and c, to then calculate the angles of each joint. Okay, so that's for the angle. So for the impact and benefits of this system, the first one is the system is able to ease the process of motion capture, where user would be just have to select the video from the system. They don't have to where all of this suit, as I've mentioned for the marker-based motion capture. The second one is it also save costs as they don't have to buy all of these extensive equipment. They just need to install this software and just give a video path for this to the system to process. And this system is useful for researchers. Maybe they want to conduct any research on body movements or various fields. And it is also useful for analysts in various industries such as healthcare, where sometimes medical assistant they need the information of the angles being performed by a test subject, or also in sports is also especially crucial when they are performing all of this fast-paced motion where they need to find the angle and velocity that the um, athletes are performing at. So um, next is the project demonstration for the system. So I'll go ahead and launch the CMD. So I launched my file using command prompt. So I've already activated the necessary conduct environment, since there are dependencies that you have to install such as OpenCV and such. Okay, so to launch the file, I'll just simply have to write the name of the file, python.method file. So click enter and it will bring it to this window. Okay, this is the first um, the logo of the system itself. Okay, so first let's just for the sake of this demonstration, let's just try to register first. So let's say I register FIRDAUS. I have to bring it here since it launches on a different screen. So this is the register window that have been pop up when I click on it. So let's say my username is FIRDAUS 981 and the password is FIRDAUS. Okay, click register and it will prompt a window of registration successful. So let's just try to log in, click login, then this window will pop up, FIRDAUS 981, and let's say we give a wrong password. Maybe I write FIRDAUS 1 and click login, and you can see that it will prompt a window of try again, invalid password. So let's just put the correct credential, 981 and FIRDAUS. Okay, click login and it will promise a success window. So click OK and then you'll move to the next window where we have to browse the video file. So all of my video files are located in one place where I put it all here in my sample video. Okay, so for this video, let's just try to process this video, and then you just click start process to begin the process, and it would then bring us to this window, okay, where it is showing that the system is processing each frame that is available in the video itself. So this would take some time to process, but I'll just click escape to further create the video. So since I've already processed this video beforehand, okay, we'll just show this is the process of it concatenating the array of images as I've mentioned earlier, because when we process the video separately for each frame, you will then have to concatenate to produce an output video. Okay, so now we have to, as I've mentioned also, to prevent from overwriting being done to existing files, we have to select the project directory and see and look for okay, I'll just show it first here. Everything I put it in one folder called metal output file. Okay, so let's say we select this directory for our project folder, and our project name, let's just say the test subject names is Hisham actually, so let's just try Hisham1. Just put Hisham first. You have to first check for the project name. Okay, as you can see in the directory that Hisham is available, so we can go ahead and create the project since it's already available. You can create it and it will promise the next one, the next window that shows this is the successfully created project file folder. Okay, then we can just simply click on it and it will launch us a file explorer window here, which has 3 files in total: the angle by frame, output, and velocity. Okay, so I will not use this one. I'll open the file that has been processed, all of it, because that one just now I just processed a few percent because it will take some time. So this is the output video, so that I'll bring it here on this window. As you can see, it's processing the video file, and you can see I've already appended all of these labels onto the respective body joints. As you can see, it's also labeled by the number. You can see, let's say for this instance, the right elbow, label 1, you can see here, it's performing a angle of 92 degrees. Okay, so this so you'll just move throughout the video, and since it has processed for each frame, this is the output video. But as you can see, certain moment of time, let's just play it again. There are certain moments where that, as you can see just now, it switches side. So this is the one of the limitation of the algorithm itself. Um, it will have a problem to uh, sometimes correctly detect, but just momentarily. I think it's because of lighting and such. That's my personal opinion. Okay, so this is the video file, and for the angle file, let's just click on it, and it will launch the Excel file. And you can see this is the top part is all of the frames, 0 1 2 3 4 5. So this video is a 60 frames per second video, and around 14 second of video. So there's around 800 frames. As you can see here, there's 855 total frames, and for each frame you can see that all of the labels that I've appended just now, it is placed onto the output file itself, and it has been labeled for every joint. So let's say for the right elbow, for the first frame, it has a 162 degree, it's performing that amount of degree in that motion for that particular joint, and so on and so forth for every joint on the test subject's body. Okay, so that's for the angle file. So let's look at the velocity file. So for the velocity, okay, so this is the file. For the velocity file, you can see here that it does not have the same amount for the frames for the angle file. This is because velocity is computed based on seconds. So it's not based on every frame, it's based on the number of seconds available in the video. So as I've mentioned earlier, that particular video has 14 seconds in it, so that's why there are 14 different frames. And for each second, I've selected only 4 different joints for the system to calculate the velocity, since left wrist, right wrist, left ankle, and right ankle are all of the 4 body parts that perform motions that are fast-paced. So I could actually include all for the elbow and shoulder and everything, but that has a lower magnitude of velocity compared to these 4 joints, body joints. So with that, okay, so let's just look at the system once again. So you can either process another video or exit the program for the last window. So let's say if I process another video, it will prompt me the window where I select the video files. And if I wish to exit, let's say if I don't want to process any more videos, you can just click exit program. And that will be the end of the project demonstration. Thank you for listening, and goodbye.